Welcome to Module 6, Compute. In this module, we will address compute services as an overview, Amazon EC2, Amazon EC2 cost optimization, container services, an introduction to AWS Lambda, an introduction to AWS Elastic Beanstalk. In addition to the topics covered in this module, there are several resources available to further your understanding of the AWS compute services, including a recorded EC2 demonstration and a hands-on lab where you practice launching EC2 instance from the AWS Management Console. You will also explore the advantages and disadvantages of running a database deployment on Amazon EC2 versus running it on Amazon Relational Database Service, RDS, as well as several activities where you will explore AWS Lambda and Elastic Beanstalk. Finally, there's a knowledge check that you will use to test your understanding of the key concepts that are covered in this module. After completing this module, you should be able to provide an overview of different AWS compute services in the cloud, demonstrate when to use Amazon Elastic Compute Cloud, Amazon EC2, identify the functionality in the EC2 console, perform basic functions in Amazon EC2 to build a virtual computing environment, identify Amazon EC2 cost optimization elements, demonstrate when to use AWS Elastic Beanstalk, demonstrate when to use AWS Lambda, and finally, identify how to run containerized applications in a cluster of managed servers. Let's get started. Welcome. This video will provide an overview of AWS compute services. AWS offers many compute services, which we cover in this module. Take a moment to review the compute services highlighted. Here's a brief summary of what each compute service offers. Amazon Elastic Compute Cloud, Amazon EC2, provides resizable virtual machines. Amazon EC2 Autoscaling supports application availability by allowing you to define conditions that will automatically launch or terminate EC2 instances. Amazon Elastic Container Registry, Amazon ECR, is used to store and retrieve Docker images. Amazon Elastic Container Service, Amazon ECS, is a container orchestration service that supports Docker. VMware Cloud on AWS enables you to provision a hybrid cloud without custom hardware. AWS Elastic Beanstalk provides a simple way to run and manage web applications. AWS Lambda is a serverless compute solution. You pay only for the compute time that you use. Amazon Elastic Kubernetes Service, Amazon EKS, enables you to run managed Kubernetes on AWS. Amazon Lightsail provides a simple-to-use service for building an application or a website. AWS Batch provides a tool for running batch jobs at any scale. AWS Fargate provides a way to run containers that reduce the need for you to manage servers or clusters. AWS Outpost provides a way to run select AWS services in your on-premises data center. AWS Serverless Application Repository provides a way to discover, deploy, and publish serverless applications. You can think of each AWS compute service as belonging to one of four broad categories defined as infrastructure as a service, compute that provides you with virtual machines, serverless computing, container-based computing, and lastly, platform as a service for web applications. In the first category, we have Amazon EC2, which provides virtual machines. Services in this category provide flexibility and leave many of the server management responsibilities to you. You choose the operating system, and you also choose the size and the resource capabilities of the servers that you launch. Amazon EC2 was one of the first AWS services, and it remains one of the most popular. In the second category, we have AWS Lambda, which is a zero administration compute platform. AWS Lambda enables you to run code without provisioning or managing servers. You only pay for the compute time that is consumed. Serverless computing is becoming more popular because it supports cloud-native architectures, which enable massive scalability at lower cost than running servers 24/7 to ensure that the same workloads can run. In the third category, we have container-based services, including Amazon Elastic Container Service, Amazon Elastic Kubernetes Service, AWS Fargate, and Amazon Elastic Container Registry. Containers are provisioned more quickly than virtual machines due to abstracting the operating system from the provisioning process. Container-based solutions continue to grow in popularity. Finally, in the fourth category, we have AWS Elastic Beanstalk, which is considered a platform as a service for web applications. AWS Elastic Beanstalk facilitates quick deployment by providing all the application services that you need. AWS manages the OS, the application server, and other infrastructure components so that you can focus on developing your application code. AWS offers many compute services as there are several different use cases. The optimal compute service or services that you will use depend on your use case. When selecting your compute service, you will want to consider the following questions. 1. What is your application design? 2. What are your usage patterns? And 3. Which configuration settings will you want to manage? Selecting the wrong compute solution for an architecture can lead to application performance, availability, or deployment issues. You can always launch a best guess design, or based on recommendations from the developers for an existing application, you can also use metrics and then collect computer-related metrics to reevaluate compute needs based on what the metrics tell you. A customer may start with one compute solution and decide to change the design based on usage patterns or changes in the application design entirely. Thanks for watching. We'll see you in the next video. Welcome. This is part 1 of the video series describing Amazon EC2. In part 1, we discuss AMIs and Amazon EC2 instance types. Running servers on premises is expensive. Servers must be purchased, data centers must be built, staffed, and maintained. Organizations must permanently provision enough hardware to handle peak workloads. After all the hardware is in place, server capacity often sits idle for significant portions of every day, which is wasteful. Amazon Elastic Compute Cloud is a different option. Amazon EC2 provides virtual machines where you can host the same applications you run on premises servers. It provides secure, resizable compute capacity in the cloud. Common uses for EC2 instances include application servers, web servers, database servers, other types of servers listed here, or even servers not listed here. Amazon EC2 provides virtual machines, or VMs, in the cloud. These VMs are referred to as EC2 instances. You have full administration control over the Windows or Linux operating system that runs on these instances. Most server operating systems are supported, including recent versions of Windows, Red Hat, SUSE, Ubuntu, and Amazon Linux. With Amazon EC2, you can launch any number of instances of any size into any availability zone, pretty much anywhere in the entire world, in a matter of minutes. Instances launch from Amazon Machine Images, or AMIs, which are effectively virtual machine templates. You can control traffic to and from these instances by using security groups. The first time you launch an Amazon EC2 instance, you will likely use the AWS Management Console Launch Instance Wizard. The Launch Instance Wizard simplifies the EC2 instance creation process. If you accept all the default settings, this allows you to skip most of the steps provided by the wizard. However, for most deployments, you'll want to modify the default settings so that the servers you launch are deployed in a way that match your specific application needs. Next, we will discuss the 9 key decisions that you must make when launching an EC2 instance. The first decision you make when using the Launch Instance Wizard is which Amazon Machine Image, or AMI, to launch the EC2 instance from. Think of an AMI as a template. The AMI contains a Windows or Linux operating system, and it will often have additional software pre-installed. You can use different AMIs to launch instances that will serve different purposes. For example, you can choose one AMI to launch an instance that will become a web server, and choose another AMI to deploy an instance that will host an application server. You can also launch multiple instances from a single AMI. When choosing an AMI from which to create your EC2 instance, there are 4 categories of AMIs available. The Quick Start category offers pre-built AMIs provisioned by AWS for launching instances. Many Linux and Windows Quick Start options are available for your use. The My AMIs category contains AMIs that you have created. I'll discuss how to create these in a moment. In the AWS Marketplace category, a catalog with thousands of software solutions built into AMIs are available for use. They can help you get started quickly for specific use cases. Finally, we have the Community AMIs category, where AMIs created by people all around the world are shared. These AMIs are not checked by AWS, so use them at your own risk. Avoid using them in any production or corporate environment. Let's take a look at how AMIs are created. Starting with step 1, you see that you can create an instance from a starter AMI such as QuickStart, or you can create an instance from a virtual machine that you imported from your on-premises data center that you turned into an AMI. Regardless of which AMI you launched the instance from, you can then connect to the instance, which is labeled unmodified instance in the diagram here, and make some modifications to it. For example, you could run a script to update the operating system with important security patches, or you might install or upgrade software on it, such as Python, Java, or other libraries. The result in this is that you come up with a modified instance. In step 3, you can then capture the modified instance as a new AMI. When you create an AMI, Amazon EC2 stops the instance, creates a snapshot of the root volume, and registers the snapshot as an AMI. After an AMI is registered, the AMI can be used to launch new instances in the same AWS region. The new AMI can now be thought as a new starter AMI. Step 4 shows how you might want to also copy the AMI to other AWS regions so that EC2 instances can also be launched to those locations as well. After you choose the AMI for launching the instance, you must next choose the instance type. AWS EC2 provides a selection of instance types optimized for different use cases. Instance types reflect combinations of CPU, memory, storage, and networking capacity. The different instance types give you flexibility to choose the most appropriate mix of resources, such as memory, processing power, disk type, network performance capabilities, as they're needed for your applications. Instance type categories include general purpose, compute optimized, memory optimized, storage optimized, and accelerated computing instances. Each instance type category offers many instance types to choose from. When comparing EC2 instance types, you will notice that instance type names consist of several parts. For example, consider the T3.large instance type. T is the family name, which is then followed by a number. The number is known as the generation number of that instance type. So a T3 instance is the third generation of the T family. In general, instance types that are of higher generation are more powerful and provide better value for the price. The next part of the name indicates the size of the instance. As you can see in the example instance's size chart, a T3.2x large has twice the processing power, or CPUs, and twice the memory as a T3x large. Instance types vary in several ways, including CPU type, CPU or core count, storage type, storage amount, memory amount, and network performance. The chart here shows the different instance categories and which instance type families and generation numbers fit into each category type. Consider a few of the instance types in more detail. T3 instances are general purpose instances that provide a baseline of CPU performance with the ability to burst above the baseline. Use cases for this type of instance include web applications, development environments, code repository, microservices, test and staging environments, and many more. C5 instances are optimized for compute-intensive workloads and deliver high performance at low price per compute ratio. Use cases include scientific modeling, batch processing, and ad serving, highly scalable multiplayer games, and video encoding. R5 instances are optimized for memory-intensive applications. Use cases include high-performance databases, data mining and data analysis, in-memory databases, real-time processes of unstructured big data, Apache Spark clusters, and other enterprise applications. In addition to considering the CPU, RAM, and storage needs of your workloads, it's also important to consider your network bandwidth requirements. Each instance type provides a documented network performance level. For example, an A1 medium instance will provide up to 10 gigabits per second, but a P3DN 24x large instance provides up to 100 gigabits per second. It is important to choose an instance type that supports your networking requirements. When you launch multiple EC2 instances, Amazon attempts to place them so that they are spread out across the underlying hardware and not all located on the same hardware. However, you can use placement groups to influence the placement of interdependent instances to meet the needs of your workload. For example, you might specify that 3 instances should all be deployed in the same availability zone to ensure lower network latency and higher network throughput between the instances. Many instance types also enable you to configure enhanced networking to get significantly higher packet per second performance, lower network jitter, and lower latencies. Thanks for watching. We'll see you in the next video. Welcome. This is part 2 of the video series describing Amazon EC2. In part 2, we discuss networking settings, attaching an IAM role, user data scripts, and storage options. After you have chosen an AMI and instance type, you must specify the network location where the EC2 instance will be deployed. The choice of region must be made before you start the Launch Instance Wizard. Verify that you are in the correct region within the Amazon EC2 console before you choose Launch Instance. Within the region, you can specify to place the instance into any existing subnet, into any existing VPC. The wizard also provides a link to create a new VPC or to create a new subnet if wanted. In the example shown here, the user has indicated that the instance should be deployed into a specific public subnet inside a specific VPC. If you do not specify a VPC when launching an instance, the instance will be placed in the default VPC. When you launch an instance in a default VPC, AWS will assign it a public IP address by default. When you launch an instance into a non-default VPC, the subnet has an attribute that determines if instances launched into it receive a public IP. If you want to, you can override this setting for the instances as you are launching them. It's common to use EC2 instances to run an application that must make API calls to other AWS services. To support these use cases, AWS allows you to create and attach an IAM role to the EC2 instance. Without this feature, you might be tempted to place AWS credentials on EC2 instances so an application can use them to call another AWS service. However, you should never store AWS credentials on an EC2 instance. It's not secure. Instead, attach an IAM role to the EC2 instance. An instance profile is a container for an IAM role. If you use the AWS Management Console to create a role for Amazon EC2, the console automatically creates an instance profile and gives it the same name as the role. In the example, you see an IAM role is attached to an EC2 instance to grant permissions to an application that runs on that instance. The application must access a bucket in Amazon S3. You can attach an IAM role when you launch the instance, but you can also attach a role to an already running EC2 instance. When you create an EC2 instance, you have the option of passing user data to the instance. User data can automate the completion of installations and configurations at instance launch. For example, a user data script might patch and update the instance operating system, fetch and install software, license keys, or install additional software. In example, user data scripts you see is a simple 3-line Linux bash shell script. The first line indicates that the script should be run by the bash shell. The second line invokes the yum utility, which is commonly used in many Linux distributions to retrieve software from an online repository and install it. The command tells yum to update all installed packages to the latest versions. Line 3 indicates that the wget utility should be installed. Wget is a common utility for downloading files from the web. For a Windows instance, the user data script should be written in a format that is compatible with a command prompt window or batch commands, or with Windows PowerShell. When the EC2 instance is created, the user data script will run during the final phases of the boot process. By default, user data only runs the first time that an instance starts up. User data scripts can be used strategically to reduce the number of custom AMIs that you need to build and maintain. For example, instead of maintaining software installations and configurations in custom AMIs, consider maintaining separate user data scripts to handle those actions at instance launch. When you launch an EC2 instance, you can configure storage options. For example, you can configure the size of the root volume where the guest operating system, such as Windows or Linux, is installed. You can also attach additional storage volumes when you launch the instance. Some AMIs are configured to launch more than one storage volume by default to provide storage options that are separate from the root volume. Each volume that your instance will have, you can specify the size of the volumes and the volume type, and whether the storage will be retained if the instance is terminated. You can also specify if encryption should be used or not. Let's look at the storage options available. Amazon Elastic Block Store, or Amazon EBS, is an easy-to-use, high-performance, durable block storage service designed to be used with Amazon EC2. Amazon EBS offers different volume types so that you can balance price and performance. If you stop an EBS-backed instance and start it again, the data will still be there. Amazon EC2 Instant Store provides temporary block-level storage for your instance. This storage is located on hard disks physically attached to the host computer. Instant Store works well when you must temporarily store information that changes frequently, such as buffers and cache. It's important to know if the instances are stopped, either because of an error or a malfunction, that the data on the Instant Store will be deleted. The root volume must run on Amazon EBS or Instant Store. However, for other storage needs, some options include Amazon Elastic File System, which provides a scalable, managed elastic network file system, and Amazon S3, which is an object storage service that offers scalability, data availability, security, and performance. Here, you see two examples of how storage options could be configured for EC2 instances. The example for instance 1 shows that the root volume, which contains the OS and possibly other data, is stored on Amazon EBS. This instance also has two attached volumes. One volume is a 500 gigabyte Amazon EBS storage volume, and the other volume is an Instant Store volume. If this instance was stopped and then started again, the OS volume would survive, and any data that was stored on either the 20 gig Amazon EBS volume or the 500 gig Amazon EBS volume would remain intact. However, any data that was stored on Ephemeral Volume 1 would be permanently lost. The example for instance 2 shows that the root volume is on an Instant Store volume type, Ephemeral Volume 2. An instance with an Instant Store root volume cannot be stopped by an Amazon EC2 API call. It can only be terminated. However, it could be stopped from within the instance OS, for example, by issuing a shutdown command, or it could be stopped because of an OS or disk failure, which would cause the instance to be terminated. If the instance was terminated, all the data that was stored on Ephemeral Volume 2 would be lost, including the OS. You would not be able to start that instance again. Therefore, do not rely on Instant Store for valuable, long-term data. Instead, use a more durable data storage such as Amazon EBS, Amazon EFS, or Amazon S3. If an instance reboots, intentionally or unintentionally, data on the Instant Store root volume is still available. Thanks for watching. We'll see you in the next video.
Welcome. This is part 3 of the video series describing Amazon EC2. In part 3, we discuss tagging, security groups, key pairs, the AWS CLI, and essential information about running instances and instance lifecycle. A tag is a label that you assign to an AWS resource, such as an EC2 instance. Each tag consists of a key and an optional value, both of which you define. Tags enable you to categorize AWS resources in different ways. For example, you might tag instances by purpose, owner, or environment. Tagging is how you can attach metadata to an EC2 instance. For example, a commonly used tag for EC2 instances is a tag key called name and a tag value that describes the instance, such as Web Server 1. The name tag is exposed by default in the Amazon EC2 console instances page. It's best practice to develop tagging strategies. Using a consistent set of tag keys makes it easier for you to manage your resources. A security group acts as a virtual firewall that controls network traffic for one or more instances. When you launch an instance, you can specify one or more security groups. Otherwise, the default security group is used. You can add rules to each security group. Rules allow traffic to or from its associated instance. When traffic attempts to reach an instance, all the rules from all the security groups that are associated with the instance are evaluated. When you define a rule, you can specify the allowable source of the network communication for inbound rules or destination for outbound rules. The source can be an IP address, an IP address range, another security group, a VPC endpoint, or anywhere, which means that all sources will be allowed. By default, a security group includes an outbound rule that allows all outbound traffic. The inbound traffic rule shown here allows secure shell or SSH traffic over TCP port 22 if the source of the request is MyIP. The MyIP address is calculated by determining what IP address you are currently connected to the AWS cloud from when you define the rule. The last important choice to make when launching an EC2 instance through the wizard is to specify a key pair. A key pair consists of a public key and a private key. It enables secure connections to an EC2 instance. When creating an EC2 instance, you can choose an existing key pair, proceed without a key pair, or create a new key pair. You must make this decision before you can choose Launch Instances and create the EC2 instance. If you create a new key pair, download it and save it in a safe location. The only opportunity you have to download and save the new private key is at the time of creation. To connect to a Windows instance, you use the private key to obtain the administrator password and then log into the EC2 instance's Windows desktop by using Remote Desktop Protocol or RDP. To establish an SSH connection from a Windows machine to an Amazon EC2 instance, you can use a tool such as PuTTY, which will require the same private key. To log into a Linux instance, for example by using SSH, you must provide the private key when you establish the connection. After you choose Launch Instances and then choose View Instances, you will see a screen that looks like the example shown here. Many of the settings that you specified during launch are visible in the description panel. Information about the available instance includes IP address and DNS address information, the instance type, the unique instance ID that was assigned to the instance, the AMI ID of the AMI that you used to launch the instance, the VPC ID, the subnet ID, and more. Many of these details provide hyperlinks that you can choose to learn more information about the resources that are relevant to the EC2 instance you launched. The Launch Instance Wizard is not the only way to launch an instance. You can also launch EC2 instances programmatically, either by using the AWS command line interface or through one of the AWS SDKs. In this example AWS CLI command, you can see a single command that specifies the minimal information that is needed to launch an instance. Let's review the details of the command. AWS invokes the AWS command line utility. EC2 invokes the EC2 service. Run-instances is the subcommand that will be run. The rest of the command specifies several parameters, including image ID, which is the AMI ID. All AMIs have a unique AMI ID. Count. You can launch more than one instance with a single command. Instance type. Specify the instance type to create, for example, a C3 large instance. Key name. In this example, we assume that my key pair already exists. Security groups. We also assume that my security group already exists. Region. AMIs exist in an AWS region, so you must specify the region where the AWS CLI will find the AMI and other referenced resources. And this is the region that the instance will be launched into. The command should successfully create an EC2 instance if the command is properly formatted, the resources that the command needs already exist, you have permissions to run the command, and you have sufficient capacity in the AWS account. If the command is successful, the API responds to the command with the instance ID and other relevant data for your application to use in subsequent API requests. As you can see, the AWS CLI is a powerful tool for programmatic access to AWS. Now that you understand how an instance is launched, let's consider the different states that an instance can be brought in throughout its lifecycle. The arrows in this diagram show actions that can be taken, and the boxes show the state the instance will enter after the action. After it's launched from an AMI, an instance will be in a pending state before it reaches a running state. An instance will also initially enter a pending state if it was stopped and then restarted. A running instance is fully booted and ready. Running instances can be rebooted. A rebooted instance stays on the same physical host, maintains the same public DNS name and public IP address, and if it has instant store volumes, it retains the data on those volumes. Running instances can also be terminated. If they are, they will enter a temporary shutting down state before they are terminated. A terminated instance remains visible in the Amazon EC2 console for a while before the virtual machine is deleted. However, you can't connect to or recover a terminated instance. Finally, instances that are backed by Amazon EBS can be stopped. They enter the stopping state before they attain the fully stopped state. A stopped instance will not incur the same cost as a running instance. Starting a stopped instance puts it back into the pending state, which moves the instance to a new host machine. A public IP address is an IPv4 address reachable from the internet. Each instance that receives a public IP address is also given an external DNS host name. Any dynamically assigned public IP address assigned to an EC2 instance will be released when the instance is stopped or terminated. When the instance is started again, it will receive a new public IP address. When a public IP address is disassociated from your instance, it is released back into the public IPv4 address pool, and you will not be able to specify that you want to reuse it. If you require a persistent public IP address, consider associating an elastic IP address with the instance. To do this, first allocate a new elastic IP address in the region where the instance exists. Then, you can associate the elastic IP address with the instance. By default, all AWS accounts are limited to 5 elastic IP addresses per region because public internet addresses are scarce. However, this is a soft limit, and you can request a limit increase. Instance metadata is data about your instance. You can view it while you're connected to the instance. In a browser, go to 169.254.169.254/latest/meta-data. The data can also be read programmatically, such as from a terminal window using the curl utility. The IP address 169.254.169.254 is a link local address, and it is valid only from the instance. Instance metadata provides much of the same information about the running instance that you can find in the AWS Management Console. For example, you can discover the public IP address, private IP address, public host name, instance ID, security groups, region, availability zone, and more. Any user data specified at instance launch can also be accessed at 169.254.169.254/latest/user-data. EC2 instance metadata can be used to configure or manage a running instance. For example, you can author a configuration script that accesses the metadata information and uses it to configure applications or OS settings. Finally, you can monitor your instances using Amazon CloudWatch, which collects and processes raw data from Amazon EC2 into near real-time metrics. These statistics are maintained for 15 months, so you can access historical information and gain a better perspective on how your web application or service is performing. By default, Amazon EC2 provides basic monitoring, which sends metric data to CloudWatch every 5 minutes. To send metric data for your instance to CloudWatch every minute, you can enable detailed monitoring. In the screenshot here, you can see that the Amazon EC2 console displays a series of graphs based on the raw data from Amazon CloudWatch. Thanks for watching. This concludes the 3-part video series on Amazon EC2. See you in the next video.
Hello everyone. In this demo video, I will show you the basic process of how to launch an Amazon EC2 instance on Management Console. First, please check if the region in the upper right corner of the Management Console is the region where you plan to launch the EC2 instance, and change it if necessary. Then, type EC2 in Management Console search window and select EC2 from the candidate list. Or click Services and Compute, then select EC2. In this process, if you have recently accessed the EC2 instance page, it will be displayed in Recently Visited pane, so you can select it from here. OK. This page is the main page for EC2 instance and the related features. You can show this page at any time by choosing EC2 Dashboard in the navigation pane on the left-hand side. If we want to launch an EC2 instance, click Launch Instance in the Launch Instance section, or go to Instance page, then click Launch Instances button. Using this page, you can set up EC2 instance you want to launch. This first setting is the name of the instance. Give this instance a display name in the Name and Tag section. This is internally registered as a tag named name. In this demo, I will name it Academy Demo. In the next section, Application and OS Images, you can choose the Amazon Machine Image or AMI to use when launching. Ready-to-use AMIs are listed under the Quick Start tab. At this time, I choose Amazon Linux on the far left, and from the Amazon Machine Image, AMI below it. Here, I'm going to choose Amazon Linux 2 AMI as a demo. This choice determines the OS in your launching EC2 instance. For your information, you can create your own AMI too. In that case, when you choose Browse More AMIs here on the right hand side, you can see My AMIs tab here, and you can choose an AMI that you have already created. Additionally, if you use an AMI sold in the marketplace, you can choose Necessary AMI under other tabs here. OK, move to the next. The third configuration is instance type. Now let's determine the instance specs here. Select the instance type from the drop-down list. At this time, I will select T2 Micro, which is default as a demo. The fourth setting is key pair. This is a setting to set the key to be used when logging into the OS of the EC2 instance after launching. When the EC2 instance is running, you can access the OS using a key set here. So it is usually set it up. If you have already created a key pair, please make sure you have access to it, then select it. Here, select Academy Demo key and Virginia that has been created. If you haven't created a key pair yet, or if you want to create a new one here, click the Create a New Key Pair link to create one. Then click the Update icon after created. Note that if you don't need to log into the OS, you can choose not to set it up, but this is not recommended. The next configuration is the network, where this instance will be launched. First, you can click the Edit button to configure network settings. Then select a VPC and the subnet within that VPC. Choosing a subnet automatically determines which availability zone the EC2 instance is placed in. I will try to log in directly later in this demo, so I will launch the instance into a public subnet that can be reached from the internet. Also, make a public IP address available. Next is a firewall, that is security groups. You can create a new one here, or if you have already created a security group, you can choose it from select existing security groups. If you are creating a new security group, set a name and description for the security group below, and set specific inbound rules. Here, Academy Demo SG has been set up, so I choose it. As I mentioned before, I will try connecting via SSH and connecting via Management Console later, and my selected Academy Demo SG allows SSH and HTTPS. The sixth configuration item is storage. Here, you can set up one or more EBS. An SSE type EBS volume is required for the root volume. For this demo, I will leave it as a default. Further, when you expand advanced details here, you can configure detail settings. In this demo, I will just show you some of them. First, check this checkbox of request spot instances if we want to launch this instance as a spot instance. Additionally, by clicking the Customize link, so you can set some conditions like spot price, etc. by yourself. In this demo, this instance will be set up as on-demand instance, so I remove this check. IAM instance profile is where you set up your IAM role. You can also create a new role here if needed. Instance auto recovery is a choice to enable the auto recovery function, which launches an instance with exactly same settings when an internal failure occurs and the instance stops. The stop hibernate behavior is the activation of the hibernate option, which also archives memory when the instance is stopped. Termination protection and stop protection are settings that prevent these operations from being accidentally performed. Tenancy is a setting required when using dedicated instances or dedicated host option. And user data text box at the bottom is a place to write a script that automatically runs only the first time this instance is started. By writing a shell script for Linux and a PowerShell script for Windows, it will only run once at the beginning. However, it is important that the script does not cause errors, since it will simply start up even if an error occurs. Also, it's a good idea to check later to see if any errors have occurred. Finally, enter how many instances you want to launch with these configurations, and click Launch Instance button. You can see Success banner here, then click View All Instances button here. After you wait for a while, the instance you just launched will be shown in this list. The status changes from pending to running, and status check will be complete. Now, after waiting for a while, the EC2 instance was successfully launched. Congratulations! Let's connect to this EC2 instance. As I mentioned before in this video, I try to connect with SSH using a key pair since I have launched a Linux instance. Then after that, I also try to connect using the EC2 Instance Connect tool on the Management Console. First, let's log in with SSH. Prepare the necessary tools in advance to connect via SSH. Here, I use PuTTY. Copy and paste the IP address or domain name of the EC2 instance. You can get it from this EC2 instance details in the Management Console. In order to get instance detail information, you can click Instance ID link. Then you can see the public IP address or public domain names here, whichever you want to use. At this moment, I will copy this IP address, then paste it. Next, set a key prepared in the key pair on the connection settings screen, which is connection, then SSH. Open the SSH. You can see auth here. Then you can see the browse button here. You can choose key pair key. Finally, set a session retention time so you don't lose connectivity as soon as you connect, which locates under connection here. You can put the number of seconds. I'll set it to 60 seconds here. Now, I'm ready to go. Let's try connecting. Click the open button here. When you access the EC2 instance first time, you are asked about it is okay to access this EC2 instance. So you can just click accept button. You will be asked for username. In the case of Amazon Linux, EC2-user is prepared, so use this username here. Congratulations! Now you can connect to the Linux OS as expected. Close this window when you disconnect. Okay, now let's try to use the connection function in the management console. Go back to the management console, choose the EC2 instance, and click Connect button at the top. This page shows some options to connect EC2 instance. At this moment, I try to use EC2 instance connect. You can see the IP address and the username here, so you can just click connect at this moment. When you log into the OS using this functionality, you have already logged in as EC2 user. Also, you can see the home directory. If you can use this way, it is easy to access the EC2 instance without any specific application. Well, when disconnecting, you can just close this window. Okay, now finally, let's delete the instance you just launched. Select the instance you want to delete, then go to the Instance State drop-down. Choose Terminate Instance. You are confirmed if it is okay to delete it, so just click Terminate. Now the instance state is changed to the shutting down. Then terminate it after a while. Now this instance has been terminated. It will appear on this list for a while, but after a while it will also disappear from this table. This concludes my demo of launching, connecting, and deleting an EC2 instance. Thank you for watching.
Welcome! This video will discuss Amazon EC2 cost optimization. Amazon offers different pricing models to choose from when you want to run EC2 instances. On-demand instances are eligible for the AWS free tier. They have the lowest upfront cost and the most flexibility. There are no upfront commitments or long-term contracts. Dedicated hosts are physical servers where instance capacity that is dedicated for your use. They enable you to use your existing software licenses such as Microsoft SQL Server, and dedicated instances are instances that you run in a virtual private cloud on hardware that is dedicated to a single customer. Reserved instance enables you to reserve computing capacity for 1-year or 3-year terms with low hourly running costs. The discounted usage price is fixed for as long as you own the reserved instance. Scheduled reserved instances enable you to purchase capacity reservations that recur on a daily, weekly, or monthly basis with a specified duration for a 1-year term. Spot instances enable you to bid on unused EC2 instance capacity, which can lower your costs. The hourly price for a spot instance fluctuates depending on the supply and demand. Your instance runs whenever the bid exceeds the current market price. It is important to note that per second billing is available, but only for on-demand instances, reserved instances, and spot instances that run on Amazon Linux or Ubuntu. Each Amazon EC2 pricing model provides a different set of benefits. On-demand instances offer low cost and flexibility with no long-term contract. Spot instances provide large scale at significantly discounted price. Reserved instances are a good choice for predictable or steady state compute needs. Dedicated hosts are a good choice when you have licensing restrictions or need to meet compliance or regulatory requirements. Let's take a closer look at the pricing options and some of the more common use cases. On-demand instance pricing works well for spiky workloads, or if you need to run a test or maybe an application for a short amount of time, for example, during a development or testing period. If your workloads are unpredictable, short-term, or spiky, on-demand instances are a good choice. Spot instances are a good choice if your application can tolerate interruption, and possibly have the spot instance be terminated with a 2-minute warning. By default, when interrupted instances are terminated, you can configure them to stop or hibernate instead. Common use cases for spot instances include fault-tolerant applications such as web servers, API backends, and big data processing. Reserved instances are a good choice when you have a long-term workload with predictable usage patterns, such as servers that you know will want to run for over a consistent amount of months or years. Dedicated hosts are a good choice when you have existing per socket, per core, or per VM licensing, and you must address specific corporate, compliance, and regulatory requirements. To optimize cost, you should consider the 4 pillars of cost optimization. First, you must right-size. That is, choose the right balance of instance types. It's important to notice that when servers can be sized down or turned off and still meet your performance requirements, that this affects cost. Second is increase elasticity. Design your deployments to reduce the amount of server capacity that sits idle by implementing deployments that are elastic, such as deployments that use automatic scaling to handle peak loads. Third, choose optimal pricing. Analyze your current usage patterns so that you can run EC2 instances with the right mix of pricing options. And finally, optimize your storage choices. Reduce unused storage overhead and choose less expensive storage options if they can still meet your storage performance requirements. Let's look at the right sizing in more detail. AWS offers more than 60 instance types and sizes. The broad selection enables customers to choose the instance that best fits their workload. It can be difficult to know where to start and what instance choice will be best for your application. Review your deployed resources and look for opportunities to downsize when possible. Use Amazon CloudWatch metrics to review CPU, RAM, storage, and network utilization and identify the instances that could be downsized. Select the most cost-effective instance available that still meets your performance requirements, and if your usage pattern will be consistent, purchase reserved instances. Let's take a closer look at increasing elasticity in more detail. Elasticity is one of the central principles of the cloud, but customers often go through a learning process to operationalize elasticity to drive cost savings. One form of elasticity is the stop or hibernate Amazon EBS-backed EC2 instances when they are not in use. Common candidates for stopping or hibernating are non-production environments, development workloads, or test workloads. For production workloads, configuring more precise and granular automatic scaling policies can help you take advantage of horizontal scaling to meet peak capacity needs and to not pay for peak capacity all the time. Let's take a look at how to identify the optimal pricing model, which is the 3rd pillar of cost optimization. The available pricing models were discussed earlier in this video. You can combine multiple purchase types to optimize pricing based on your current and forecast capacity needs. You are also encouraged to consider your application architecture. For example, does the functionality provided by your application need to run on EC2 virtual machines? Or could you significantly reduce your costs by using AWS Lambda instead? AWS Lambda is discussed later in this module. Finally, let's review the 4th pillar of cost optimization in more detail. Optimizing storage choices. It's a best practice to try to reduce costs while also maintaining storage performance and availability. One way you can accomplish this is by resizing EBS volumes. For example, if you originally provisioned a 500 gig volume for an EC2 instance that will only need a maximum of 20 gig of storage space, you can reduce the size of the volume and save on costs. There are also a variety of EBS volume types available. Choose the most cost-effective type that still meets your performance requirements. Customers often use EBS snapshots to create data backups. However, some customers forget to delete snapshots that are no longer needed. Delete these unneeded snapshots to save on storage costs. Finally, identify the most appropriate destination for specific types of data. Does your application need the data that it uses to reside on Amazon EBS? Would the application run equally as well if it used Amazon S3 for storage instead? Configuring data lifecycle policies can also reduce costs. For example, you might automate the migration of older, infrequently used data to more cost-effective storage locations such as Amazon Simple Storage Service, Glacier. Done correctly, cost optimization is not a one-time process that a customer completes. Instead, you should routinely measure and analyze your systems so that you can continually improve and adjust your costs. Tagging helps provide information about what your resources are being used and by whom and for what purpose. You can activate cost allocation tags in the Billing and Cost Management console, and AWS can generate a cost allocation report based on your assigned tags. Apply tags that represent business categories to organize your costs across multiple services. Also consider using AWS services such as AWS Trusted Advisor, which provides real-time guidance to help you provision resources that follow AWS best practices. Encourage teams to architect for cost. AWS Cost Explorer is a free tool that you can use to view graphs of your costs. Finally, cost optimization efforts are typically more successful when the responsibility for cost optimization is assigned to an individual or a team. Thank you for watching. We'll see you in the next video.
Welcome. This video will provide an overview of AWS container services. You may be thinking, what are containers? Containers are a method of operating system virtualization. Containers are smaller than virtual machines and do not contain an entire operating system. Instead, containers share a virtualized operating system and run as resource-isolated processes. Containers offer several benefits. First, they support repeatability. Additionally, containers deliver environmental consistency because the application's code, configurations, and dependencies are packaged into self-contained environments. Next, they can help ensure that applications deploy quickly, reliably, and consistently, regardless of the deployment environment. Lastly, in terms of space, container images are usually an order of magnitude smaller than virtual machines. Spinning up a container happens in hundreds of milliseconds, resulting in faster launch times than traditional virtual machines. In order to understand containers, it's helpful to know a little bit about Docker. Docker is a software platform that packages software, such as applications, into containers. Docker is installed on each server that will host containers, and it provides simple commands that you can use to build, start, or stop containers. Containers are created from templates called Docker images. Containers have everything that an application that you want to run needs, including libraries, system tools, and the application code, as well as any runtime libraries. Many people who are first introduced to the concept of a container think that the containers are exactly like virtual machines. However, there are some key differences. One significant difference is that virtual machines run directly on a hypervisor, while containers run on any operating system if they have the appropriate kernel features to support Docker host software and the Docker daemon is present. The right of the diagram shows a virtual machine VM-based deployment. Each of the 3 EC2 instances runs directly on the hypervisor that is provided by the AWS Global Infrastructure. Each EC2 instance is a virtual machine. In this VM-based deployment, each of the 3 apps runs on its own VM, and each VM provides process isolation. The left of the diagram shows a container-based deployment. Here you see that only one EC2 instance runs a virtual machine. The Docker engine is installed on the Linux guest OS of the EC2 instance, and that there are 3 containers. In this container-based deployment, each app runs its own container, which provides the process isolation, but all the containers run on a single EC2 instance. The Docker engine is present to manage how the containers interact with the Linux guest OS, and it also provides central management functions throughout the container lifecycle. In an actual container-based deployment, a large EC2 instance could run hundreds of containers. Given what you now know about containers, you could launch one or more Amazon EC2 instances, install Docker on each instance, and manage and run the Docker containers on those Amazon EC2 instances yourself. While that's an option, AWS provides a service called Amazon Elastic Container Service, or Amazon ECS, that simplifies container management. Amazon ECS is a scalable, high-performance container management service that orchestrates the running of Docker containers. It manages the fleet of nodes, or EC2 instances, that run your containers, removing the complexity of managing the infrastructure yourself. Amazon ECS provides a familiar set of features to anyone who uses the EC2 service, including elastic load balancing, security groups, EBS volumes, and IAM roles. Let's look at the role Amazon ECS plays with regards to containers. To prepare your application, you create a task definition, which is considered a blueprint for your application. Task definitions specify details such as which containers should be deployed to run the task. You specify the number of tasks that will run on your cluster, and Amazon ECS Task Scheduler is responsible for placing tasks within your cluster. When Amazon ECS runs the container based on your task, it places them on an ECS cluster. When you choose the EC2 launch type, the cluster consists of a group of EC2 instances, each of which is running an Amazon ECS container agent. In the example here, the Amazon ECS Task Scheduler has received a request to run a task that will require 3 instances of container A and 2 instances of container B. Amazon ECS places these 5 containers on the EC2 instances and the ECS cluster. They're distributed in a way that accounts for the CPU and memory capacity available on the cluster nodes. When you create an Amazon ECS cluster, you need to decide the type of cluster you want. You need to ask yourself, do you want to manage the cluster? If you answer yes, you'll have a more granular control over the cluster, and the cluster will run on EC2 instances that you manage. To manage the cluster yourself, choose either the EC2 Linux plus networking or the EC2 Windows plus networking cluster option. You'll need to specify details about the EC2 instances that will make up your cluster. The same details you specified when launching a standalone EC2 instance. If you don't want to manage the cluster yourself, choose the Create a Networking Only cluster option. Networking only Amazon ECS clusters are powered by AWS Fargate. With the Fargate launch type, the cluster that will run your container will be managed by AWS. With this option, you only need to package your application in containers, specify the CPU and memory requirements, define networking and IAM policies, and launch the application. You do not need to provision, configure, or scale the cluster. It removes the need to choose server types when you decide to scale your clusters or optimize cluster packaging. The Fargate option enables you to focus on designing and building your applications. Next, we'll discuss an alternative container service to Amazon ECS. However, before we begin, it's important to have a general understanding of Kubernetes. Kubernetes is an open source software for container orchestration. Kubernetes enables you to deploy and manage containerized applications at scale. With Kubernetes, you can run any type of containerized application by using the same toolset in both on-premise and your data center, including the cloud. Kubernetes can work with many orchestration containerized technologies, including Docker. Because it is a popular open source project, a large community of developers and companies build extensions, integrations, and plugins that keep the software relevant, resulting in new and in-demand features being added frequently. Kubernetes also automates container provisioning, the networking configuration of containers it deploys and manages, the load distribution of containers, and scaling to handle application load. You may be thinking that you can launch one or more Amazon EC2 instances, install Docker on each instance, then install Kubernetes on the cluster, all while being able to manage the Kubernetes instances yourself. While that is an option, Amazon Elastic Kubernetes Service, or Amazon EKS, significantly simplifies the management of Kubernetes clusters. Amazon EKS makes it easy for you to run Kubernetes on AWS without needing to install, operate, and maintain your own Kubernetes control plan. Amazon EKS is certified Kubernetes conformant, so existing applications that run on upstream Kubernetes are compatible with Amazon EKS. It supports Linux and Windows containers, and it's compatible with Kubernetes community tools and many popular add-ons. You may be wondering why Amazon offers both Amazon ECS and Amazon EKS, as they are both capable of orchestrating Docker containers. Well, the reason that both services exist is to provide customers with flexible options. You can decide which option best matches your needs. One challenge of deploying applications on containers is keeping track of storing and managing all those containers. To keep addressing this challenge, AWS provides the Amazon Elastic Container Registry, or Amazon ECR service. It is a fully managed Docker container registry that makes it easy for developers to store, manage, and deploy Docker container images. It is integrated with Amazon ECS, so you can store, run, and manage container images for your applications that run on Amazon ECS. When you specify the Amazon ECR repository in your task definition, Amazon ECS will retrieve the appropriate images for your applications. Amazon ECR supports team collaboration, access control, and third-party integration. And it's also possible to use Amazon ECR images with Amazon EKS. Thank you for watching. We'll see you in the next video. Welcome. This video will provide an introduction to the AWS Lambda service. AWS offers many compute options. For example, Amazon EC2 provides virtual machines, while both Amazon ECS and Amazon EKS offer container-based compute services. However, there is another approach to compute that does not require you to provision or manage servers. This third approach is often referred to as serverless computing. AWS Lambda is an event-driven serverless compute service. Lambda enables you to run code without provisioning or managing servers. You create a Lambda function, which is the AWS resource that contains the code that you want to run. You then set the Lambda function to be triggered either on a schedule or in response to an event. Your code only runs when it's triggered. You pay only for the compute time you consume. You are not charged when your code is not running. With Lambda, there are no new languages, tools, or frameworks to learn. Lambda supports multiple programming languages, including Java, Go, PowerShell, Node.js, C#, Python, and Ruby. Lambda completely automates the administration. It manages all the infrastructure to run your code on highly available, fault-tolerant infrastructure, which enables you to focus on building differentiated back-end services. Lambda provides built-in fault tolerance. It maintains compute capacity across multiple availability zones in each region to help protect your code against individual machine failures or data center failures. You can orchestrate multiple Lambda functions for complex or long-running tasks by building workflows with AWS step functions. With step functions in Lambda, you can build stateful, long-running processes for applications and backends. Finally, with Lambda, you pay only for the requests that are served and the compute time that is required to run your code. Billing is metered in increments of 100 milliseconds, which makes it cost-effective to run code on AWS Lambda. Lambda functions are triggered by event sources. An event source can be an AWS service or developer-created application that produces events that trigger the AWS Lambda function to run. Some services, such as Amazon S3 and Amazon CloudWatch Events, publish events to Lambda by invoking the Lambda function directly. Other services are pulled by Lambda. For example, Lambda can pull records from an Amazon Simple Queue service, and Lambda can read events from the Amazon DynamoDB database service. Finally, some services, such as Elastic Load Balancing and Amazon API Gateway, can invoke your Lambda function directly. You can also invoke functions directly from the Lambda console or via API, SDK, or the AWS CLI. Direct invocation can be useful, for example, when you are developing a mobile app and want the app to call Lambda functions. AWS Lambda also automatically monitors functions by using Amazon CloudWatch to assist you to troubleshoot failures in a function. Lambda logs all requests handled by your function. Now that you know that a Lambda function is a custom code that you write to process events, and that Lambda runs the Lambda function on your behalf, let's consider how you configure Lambda functions. When you use the AWS Management Console to create a Lambda function, you first give the function a name. Then you specify the runtime environment the function will use. For example, a version of Python or Node.js. You also specify an execution role to grant IAM permission to the function so that it can interact with other AWS services as necessary. Next, you configure the function. Configurations include adding a trigger. You specify one of the available event sources. Add your function code, either by using the provided code editor or uploading a file that contains your code. Specify the memory in megabytes to allocate to your function. Optionally, specify environment variables, such as timeout, the specific VPC to run the function in, and other settings. All of the settings just mentioned end up in a Lambda deployment package, which is a zip archive that contains your function code and dependencies. When you use the Lambda console to author your function, the console manages the package for you. However, if you use the Lambda API to manage functions, you need to create a deployment package yourself. Consider an example use case for a schedule-based Lambda function. Say that you're in a situation where you want to reduce your Amazon EC2 usage. You decide that you want to stop instances at a predefined time, for example, at night when no one is accessing them. And then you want to start the instances back up in the morning before the workday starts. In this situation, you could configure an AWS Lambda and Amazon CloudWatch events to help you accomplish these actions automatically. Here's what happens at each step in the example. First, a CloudWatch event is scheduled to run a Lambda function to stop your EC2 instances at the end of the workday. Second, the Lambda function is triggered and run with the IAM role that gives the function permission to stop the EC2 instances. Third, the EC2 instances enter the stopped state. Fourth, at the start of the workday, a CloudWatch event is scheduled to run a Lambda function to start the EC2 instances. Fifth, the Lambda function is triggered and run. And finally, the EC2 instances enter the running state. Now consider an example use case for an event-driven Lambda function. Suppose you want to create a thumbnail for each image file that's uploaded to an S3 bucket. To build a solution, you create a Lambda function that Amazon S3 invokes when objects are uploaded. The Lambda function reads the image object from the source bucket and creates a thumbnail image in a target bucket. AWS Lambda has some limits that you should know about. First, Lambda limits the amount of compute and storage resources you can use to run and store functions. Lambda also limits you to 1,000 concurrent invocations in a region. Lambda functions can be configured to run up to 15 minutes at a time. You can set the timeout to any value between 1 second and 15 minutes. There is a 250 megabyte limit on the deployment package size of a Lambda function. A layer is a zip archive that contains libraries or other dependencies. With layers, you can use libraries in your function without needing to include them in your deployment package. Limits are either soft or hard. Soft limits can potentially be relaxed by submitting a support ticket and providing justification for the request. Hard limits cannot be increased. Thanks for watching. We'll see you in the next video.
Welcome. In this video, we'll provide an introduction to the AWS Elastic Beanstalk service. Elastic Beanstalk is another AWS Compute Service option. It provides an easy way to get web applications up and running on the AWS cloud. AWS Elastic Beanstalk automatically handles infrastructure provisioning and configuration, deployment, load balancing, automatic scaling, health monitoring, analysis and debugging, and logging. You upload your code and Elastic Beanstalk automatically handles the deployment, from capacity provisioning to load balancing to automatic scaling and monitoring and application health. When you use AWS Elastic Beanstalk, you retain full control over the AWS resources that power your application, and you can choose to access the underlying resources at any time. There is no additional charge for AWS Elastic Beanstalk. You only pay for the AWS resources, such as EC2 or S3 buckets, that you create and store and run your application on. You only pay for what you use, as you use it. AWS Elastic Beanstalk enables you to deploy your code through the AWS Management Console, the AWS Command Line Interface, Visual Studio, or Eclipse. It supports a broad range of platforms, including Java, .NET, PHP, Node.js, Python, Ruby, Go, and Docker. Elastic Beanstalk provides all the application services that you need for your application. The only thing you must create is your code. AWS Elastic Beanstalk deploys your code on several popular application web servers. In summary, Elastic Beanstalk is fast and simple to start using. You use the AWS Management Console, a Git repository, or an IDE such as Eclipse or Visual Studio to upload your application. You can improve developer productivity by focusing on writing code instead of managing and configuring servers, databases, load balancers, firewalls, and networks. Elastic Beanstalk is also difficult to outgrow. Your application can handle peaks in workload or traffic. It automatically scales your application up and down based on your application's specific needs by using easily adjustable automatic scaling settings. You can even use CPU utilization metrics to trigger automatic scaling actions. Finally, you have the freedom to select the AWS resources, such as Amazon EC2 instance type, that are optimal for your application. Elastic Beanstalk enables you to retain full control over the AWS resources that power your application. If you decide that you want to take over some or all of the elements of your infrastructure, you can do so by using the management capabilities that are provided by Elastic Beanstalk. Thank you for watching. We'll see you in the next video.